Welcome back. Today we're going to look at sections 2.8 and 2.9 from the text covering these basic topics, subspaces, the basis, dimension, and rank. Again, we'll see that these are all related to matrices, and we'll see that they're all related to row-reducing matrices, our favorite pastime as far as linear algebra is concerned. And so let's just jump right in and talk about what I mean when I say the word subspace. So I'm going to give a formal definition, and then we're going to look at how that applies to real situations in terms of Rn, and then R2 and R3, some of our favorite spaces where we can draw pictures. So a subspace definition. A subspace of Rn is a subset, let's call it H, for which the following is true. The zero vector is in H. So all I'm doing is picking out a whole bunch of vectors. In order for it to be a subspace, one of those vectors that I pick out has to be the zero vector. 2, if x and y are in H, then so is x plus y. So if I have any vectors that are in the set that I start with, and then I add them up, then the resulting vector that I get, x plus y, also has to be there. And then finally, if x is in H, then any scaled version of x is also in H. Then Cx is in H for all C real numbers. All right, so we have a couple of, so what we say here is this is, we say that H is closed under addition and scaling. So when I say that a set is closed under some operation, I mean that if I apply the operation to things that are in the set, it stays in the set. So let's look at some things that are subspaces and some things that aren't subspaces. So this is some examples of different things. So here's R2. Let's look at this line. All right, so this line is a subset of R2, but it's not a subspace, first of all, because it doesn't include the zero vector. So if this is H, H is the line, then 0 is not in H, so H is not a subspace. All right. What if I made a line that did include 0? Here's R2. What if I looked at all vectors that are on this line? Well, now 0 is in there, so that's good. The 0 vector is there. If I have two vectors that are on this line, if I take vector v1, which is on the line, and I take vector v2, which is also on the line, and I add them up, well, what happens? Remember, when I add vectors, if I take v1 plus v2, I take the whole vector v2 and attach it to the end of v1, and it would still be on the line. So by adding up two vectors that are on this straight line, I get another vector which is still on that same line. So this one is closed under addition. That is, if I add two vectors, it stays on the line. It's also clearly closed under scaling. If I take vector v1 and I scale it by anything, positive or negative, to turn it into the other direction, then it still stays on the line. So it's also closed under scaling. So yes, it is a subspace. Let's say that H is the first quadrant. Is that a subspace? And let's include everything on the axes in the first quadrant as well. So that it does include the zero vector. So zero vectors in there. If I take two vectors which point in the first quadrant and I add them up, well, the vector that I get back is still in the first quadrant. So 0 is in H, and it's closed under addition. That is, if I add up two vectors that are in the set, it stays in the set. However, it is not closed under scaling. If I took this vector and I scaled it, it feels like it stays in the first quadrant, but that scaling has got to be true for any real number, positive or negative. If I scale one of these vectors by a negative value, well, that turns it back into this quadrant, and that's not in H. But it isn't, so it is not closed under scaling by negatives. So it is not a subspace. So maybe you say, well, what if I look at not just the first quadrant? If the problem is closed under scaling and I need to include the negative scaled versions, well, how about if we look at the first and third quadrants together? So let's say that H is first and third quadrants. Now 0's in H, and we've set it up so that it's closed under scaling. If I take a vector that's up here and I scale it by a positive number, well, it stays in the first quadrant. If I scale it by a negative number, well, that pushes it to the third quadrant, but since we've included the third quadrant, everything is good to go. So it's closed under scaling. However, it's not closed under addition, because if I take this vector, v1, well, let's call it w1, and I take this vector, w2, and I add them up, well, then it's over here. So by taking two vectors that are in the set and adding them up, it goes outside of the set. So it is not closed under addition. So it is not a subspace. I'm not going to prove this here, but here are some facts about subspaces of R2. There's only a few options. The set which only includes the zero vector, well, that's a subspace. Because if I take the set that only has the zero vector, well, it certainly has a zero vector. It's also closed under scaling, because if I scale 0 by anything, I get 0. It's also closed under addition, because if I add 0 plus 0, I still get 0. So that's a subspace. Another subspace is a line through the origin. We talked about that. The only other subspace is all of R2. We notice that if we try to include the first quadrant, it doesn't work because we would need to include the negative versions. But if I try to include the first and third, that doesn't work because by addition, I can get into the second quadrant. Similarly, I could get into the the fourth quadrant. And so as it turns out, if I include anything else other than just a straight line through the origin, in order to satisfy the definitions of a subspace, you need to include everything. And so these are the only subspaces of R2. And that's it. There are no other subspaces. For R3, we have a few other things. We still have the 0 set, the set that just has the origin in it. That's a subspace. Even if we're in R3, a line through the origin is still okay. I can still scale it and it stays on the line. If I add up two vectors in the same direction, the resultant vector still points in the same direction. But because now we've added more space, we've got space to work with rather than just a plane, we have an analogous line through the origin that turns to a plane through the origin. Because if I have x, y, z, and I look at a plane that goes through the origin, so if I have a plane going through the origin and I add up two vectors that are on that plane, well, the resultant vector stays on the plane. If I scale to a vector that's on the plane, it still is on the plane. So a plane through the origin is, in fact, the subspace of R3. But after that, there's no other space to go. As soon as you move off of that plane, if you would, in order to satisfy the definitions, you've actually got to include everything. So these are the only subspaces of R3. We can talk about analogous situations for higher dimensions, but the words, we start losing words, and we have to talk about hyperplanes, which are essentially, a plane is a version of R2, if you want to think about it like that. It's a flat piece which only has two different directions to it. So in R4, we can talk about a subspace which has three possible directions to it. And we'll look at that a little bit more closely in the future. But these are all of the subspaces of R3. Let's start with a matrix and talk about some specific subspaces that come out of a given matrix. All right, so what we're going to look at now is what we're going to call the column space of a matrix. Okay, so given matrix A. The column space is the set of all linear combinations of its column vectors. All right, so I have a matrix, I have the vectors that make up its columns. If I look at all linear combinations, and we'll see that that is in fact a column space. So let me remind you what I mean even by linear combinations. Recall, if I have vectors v1 and v2 and v3, a linear combination of v1, v2, v3 is just an added up version where each of these might be scaled by different factors, by different scaling factors. Is C1 v1 plus C2 v2 plus C3 v3. That's a linear combination where C1, C2, and C3 can be anything I want them to be. Okay, so let's see, why is that in fact a subspace? If I take linear combinations of vectors, why is that a subspace? All right, so my claim is that for any set of vectors, v1 through vk, they might come from columns of a matrix. That's what we're looking at here. The column space of a matrix will be the linear combinations of its column vectors. But for any set of vectors, v1 through vk, the set of all linear combinations is in fact a subspace. That's my claim. So this is the set of all C1, V1 plus C2, V2 plus all the way to CK, VK. That's what we're looking at. But 0 is certainly in here because I'm allowed to dial these C1s and C2s to be anything I want. So I can set all of the C1s through CK to be 0. So if every C1 through CK is 0, well then that's a linear combination of these vectors, and I get the 0 vector back. 0, let's call this H. So the set of all linear combinations, let's call that H. Then 0 is in H, because I can let C1 to be C2 to be all the way to CK. I can set them all to equal 0. If I took a vector that looked like this and I scaled it by anything, by 10, well then I'd simply scale each of those coefficients, scale each of those component pieces, and I'd still get a combination where I have a constant times V1, constant times V2, and so on, all added up. I'd get a linear combination of the vectors V1 through Vk. So it's also clearly closed under scaling. So let's say C times C1 V1 all the way to CK Vk is C times C1 V1 plus all the way to C CK Vk. And the point here is that these things are all this is a linear combination of V1 through Vk, because I've just got a scale version of each of V1 through Vk added up. I just changed the scale. It's also closed under addition. Because if I took two of these things, if I took C1 V1 plus all the way to CK Vk, and I added this to another linear combination, let's call it D1 V1 all the way to DK Vk. Then what I get is C1 plus D1 V1 plus all the way to CK plus DK Vk. And that's another linear combination of V1 through Vk. So it's closed under addition. And so in fact, all three of the definitions, pieces of a subspace are satisfied, and I can say H is a subspace. Now, we'll go back to the column space of a matrix, but before we do that, we need to talk about the idea of a basis. Right, a basis. A basis for a subspace, again, I'll give a definition, and then we'll look more in detail about how it actually works. A basis for a subspace H is a linearly independent spanning set remember, a spanning set is a set of vectors which makes H. So if I look at a whole bunch of vectors and I look at all possible linear combinations of those vectors and I get to H, then that's a spanning set. Okay, so here's a couple of ideas. So let's let H be the span, that is the set of all linear combinations of the vectors 1, 2, minus 1, 0, 1, 3, 1, 1, minus 4. So H is the span of these vectors. By the way, another way of saying that is that H would be the column space of the matrix given by these vectors. Because the column space is the set of all linear combinations of the columns, and that's exactly what span means. Span means all linear combinations of a set of vectors. So if H is this, a basis is a linearly independent spanning set. So we can ask, are these vectors linearly independent? This is a spanning set. Are they linearly independent? Well, let's remember how we answer that question. We make the matrix, and we row reduce. So let's just, so break out your calculators, and I'm not going to put this on the screen, but I'm just going to make this matrix and row reduce and see what I get. So this is a 3 by 3 matrix. And if I row reduce it, what I get is the following. So that's the reduced row echelon form of that matrix. In order to be linearly independent, we need to have a pivot in every column. So this is a non-pivot column. We have no pivot, so they are not linearly independent. What does that really mean here? Right, so notice what this means. This column corresponds to, we want to think about this as a free variable column. This is not really a system of equations. It is not a system of equations at this point. We don't have a constant column at the end. But this one is, if we did, we would think about this one as being the free variable. That is so what does this mean? Right, so this means that I can say, so suppose that I had, remember, let's call this V1, V2, V3. So suppose I started with the vector equation, C1 V1 plus C2 V2 plus C3 V3, and I tried to get it to be equal to 0. To be linearly independent, the only way to make that happen is if C1, C2, C3 are all 0. Right? But we discovered that that's actually not the case. So that's the same thing as looking at the matrix equation, V1, V2, V3, multiplied by the vector C1, C2, C3 to get the 0 vector back, which is actually the same thing. So that as making, how would we solve this matrix equation? We'd solve that matrix equation by looking at 1, 2, minus 1, 0, 1, 3, 1, 1, minus 4. Now we have a system of equations. The zeros correspond to the 0 vector. Row reducing, well, we just row reduce. That column of zeros at the end doesn't change anything. When we row reduce, what we got was 1, 0, 0, 0, 1, 0, 1 minus 1, 0, 0, 0, 0. Now we can talk about this as being a free variable. Which means what we get is that we actually get, since we have a free variable, what we get is a non-trivial solution. Which is to say that C1, C2, C3 are not all 0. So in fact, these are not linearly independent. But remember what that means. What it means to be linearly independent, or let's look at it from the other way around. What it means to be linearly dependent is that you can make one of the vectors as a linear combination of the others. So what this means is, so let's note that V3 was actually V1 minus V2. So if you look at the vectors that we had, vector V1 was 1, 2, minus 1. V2 was 0, 1, 3. V3 was 1, 1, minus 4. So if I take these, I subtract, then I get this. So what this means is V3 was not necessary. I didn't need it. I could create it out of V1 and V2. So since I didn't actually need V3, that's the one that made this set not linearly independent. V1 and V2 are linearly independent, and I don't need them. I can make V3 out of them, which means that I can conclude that a basis for H is instead just the two vectors that I needed, V1 and V2. I don't need the third one because I can make it out of the first two. And I don't need the third one, and I know it's the third one that I don't need because that's the one that corresponded to a non-pivot column. Right, so these were the pivot columns. The ones that are not pivot columns are the ones that correspond to free variables, which means I actually don't need them. I can make them out of the others. The other ones are linearly independent. So let's just do a simplified version of that problem. Let's find a basis for H, which is the column space of the matrix A okay. So here's A. Column space of A we're going to write as col A. And col A is the span of the column vectors of A, which is the set of all linear combinations. So as always, all we're going to do is take A and we're going to row reduce it. So I'm going to put this into my calculator. That's 4 by 4. And then I row reduce. And this is what I get. Pivot, 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 non-pivot. The basis for a span of a set of vectors is all of the vectors that I actually need. So I don't need all of these because I don't have a pivot in every column. I only need the first 3. So the basis is just the first 3. All right. The null space. The null space is a little bit different. Again, we're going to start with the matrix and we're going to come up with a subspace based on that matrix and then discover how we can write down a basis for a null space for a given matrix. So let's look at this, right? So we're going to start with the matrix A. Let's consider all vectors x with ax equals 0. 0 for empty for null. Null space is the word null comes from the fact that we're setting ax equal to 0. So I'm looking for all vectors which get sent to 0 under the linear transformation given by the matrix A. So everything that gets sent to 0. So notice that A times 0 is 0, A times this, and for any vector 0, anything times it is a 0. So let's call H all vectors. So we're gonna call this the set H. H is all vectors with AX equals 0. So 0 is an H because A times 0 is 0. Notice that A times CV, let's say that if V is in H, then A times CV is C times AV, which is C times 0, because AV is 0, because V is in H. So that means this is 0. So it's closed under scaling. And if V and W are both in H, then A times V plus W is AV plus AW. But if these are both in H, that means that AV is 0 and AW is 0. So I get 0 plus 0, which is 0. So everything that gets sent to 0 is in fact a subspace because it satisfies the 3 definition pieces of being a subspace. Okay, so if I'm going to be looking at A times X, let's think about what the dimensions of X should be. Since this has two columns, remember whatever X has to match exactly up to these numbers, so I better have 2 entries here. So is this vector X in the null space of A, which we're going to write as null A? Well, this is a pretty easy thing to answer. I just need to say, what is A times X? If I get 0 back, then the answer is yes. If I don't get 0 back, then the answer is no. Well, let's just try. I get 1 minus 3, which is negative 2, and that's all I need to know. I don't even care about the rest of this stuff. It's not 0. The 0 vector is the vector that has 0 everywhere. We can write it down. Negative 2 plus 1 is negative 1. 1 plus negative 2 is negative 1. But that's not 0, so no. Okay, so let's do better than that. So for this matrix, let's find a basis for the null space of A. Well, X is in the null space of A if AX equals 0. So we're looking at this equation, AX equals 0. But we know how to solve any matrix equation, AX equals B. We take the matrix A, we include the matrix B as the constants, and we row reduce. So let's just do that and see what we get. What we get is the following result. So if I wanted to just describe, so I could have asked this question a bunch of sections ago. Describe all solutions to this system of equations. And let's take that and describe it in parametric vector form. So if I took this and turned it into a description of the solution in parametric vector form, this is x1, x2, x3 constants. I get x1 plus x3 is 0. I get x2 plus 2x3 is 0. And I get that x3 is free. So let's call that t. X3 is our free variable. This is consistent because the bottom doesn't read something like 0 equals 1. So that tells me that x1 is negative x3, which is negative t. Tells me that x2 is negative 2t, and x3 is t, which means that the vector x, which is x1, x2, x3, is the vector negative t, negative 2t, t, which is t times negative 1, negative 2, 1. So this describes all possible vectors x which are in the null space. And so that tells me that every possible vector x is just a scaled version of the vector minus 1, 2, minus 2, 1. This is all linear combinations of this single vector because I have only one free variable x3. And so what that tells me that null A is in fact the span of just that single vector, minus 1, minus 2, 1. Because if I took this and asked for the span of a single vector, I'm asking for all scaled versions of that single vector. So a basis for the null space of the matrix is given by looking at the parametric form, vector form solution to AX equals 0 and pulling off the vectors that we get. Let's look at one that is a little bit more complicated. It'll give us more than just one vector. Okay, so here's our matrix A. Let's find a basis for null A. So we're looking at AX equals 0. So we're looking at minus 1, 0, minus 1, 2, 3, 2, 1, minus 1, 2, 2, 0, 1, 1, 2, minus 1, 3, 0, 0, 0, 0, and we row reduce. So we'll just simply put our matrix in. That's 4 by 5. And we row reduce. And what we get is the following. So now we're going to have two free variables. Free variable, free variable. Let's continue and write our solution to AX equals 0 in parametric vector form. So this is x3, this is x4. So we see that 1x1 plus x3 plus 2x4 is 0. And x2 is plus x3 plus x4 is 0. And then x3 and x4 are free. So that's called x3t and x4s. So this becomes x1 is negative t plus 2s plus negative 2s, negative t minus 2s. x2 is negative t minus s. x3 is t, x4 is s. So x is x1, x2, x3, x4 is minus t minus 2s minus t minus s ts. When I write this in parametric vector form, I need to break it apart. Each free variable will correspond to a single vector. So I need a t times the constants that belong with t, minus 1, minus 1, 1, 0. There's no t at all here. Plus s times the constants that belong with s, minus 2, minus 1, 0, 1. But again, x is all vectors which satisfy ax equals 0. And what we see is all linear combinations of now two vectors. This is all scaled and summed versions of these two vectors, which means that these two vectors are in fact the basis for the null space of the matrix. So these form a basis. Okay, now let's notice something. So the number of vectors that showed up in the basis for the column space of A, how many vectors do I get for the column space of A? Well, remember what we did was we row reduced A, we found out where the pivots were, and we took the vectors off of the original matrix A that corresponded to the pivot columns. So this is the columns of A corresponding to pivot positions. And the null space of A, well, it's not the columns of the original matrix A, but how many of them do we have? Well, for every free variable, we get a vector back that belongs in the null space of A that we use. All right, so each free variable gives a vector in the basis. Which means if I take the number of vectors that are in a basis for the column space, that's all pivots, and then I take the number of vectors that are in a basis for the null space, that's all free variables, which is all non-pivots, I get the number of columns of the matrix A that I started with. All right, so the number of vectors in the basis for col A plus number of vectors in basis for null A is equal to the number of columns of A. Okay. Two more ideas we're going to talk about from these two sections. The first is called dimension. And we're really right at a good point to talk about it. The dimension, again, I'll give a definition. The dimension of a subspace is the number of vectors that it takes in a basis. Remember, a basis is a linearly independent spanning set. All right, so for a matrix A, in order to get the column space of A, we went down and we found out where the pivots were, and we took the original vectors off of the columns of A that corresponded to the pivot columns. And so the dimension in that case In this case, so if H is the span, is the column space of A, then the dimension of H is the number of pivot columns. Number of pivots. And so related to that, just because we see this show up so often with a matrix, the rank of a matrix A is the dimension of the column space, which is the number of pivots. And the nullity of A is the dimension of the null space, which is the number of non-pivots. These things are usually generally pretty easy to actually find. Let's find rank A and the nullity of A for this matrix. Okay. So all we're going to do is row reduce the matrix and see what we get. If I row reduce this matrix, this is what I get. Remember, I haven't added a column of zeros here, so this is okay. This 0, 0, 1 does not mean inconsistent because I don't have a system of equations here. This is just a matrix that's been row reduced. But so where are the pivots? Pivot, pivot, pivot. 3 pivots. So rank A is 3. Nullity of A is the number of non-pivots, which is none here. So the nullity of A is 0. Which means we can add to our understanding of what it means to be an invertible matrix. So we made a big long theorem about everything that we've looked at in terms of linear transformations corresponding to a matrix. I'm going to add one step to this, which is to say that A is invertible. Remember that A is invertible if it has a pivot in every column, if it row reduces to the identity, if its linear transformation is one-to-one and onto, all of these things put together. But if it row reduces to the identity that it has a pivot in every column, which means its rank is the rank of A is just as big as it could be. So A is invertible if and only if, so let's say that it's square, right? A square matrix A. So that's the only way it could be an invertible. So let's say that it's n by n. So square n by n matrix A is invertible if and only if its rank is as big as it possibly could be, which is n. Finally, for today, we need to look at one last notion, which is coordinates relative to a basis. So let's start in R2. Let's notice that the vectors 1, 0, and 1, 1 actually form a basis for R2. So here's 1, 0, and here's 1, 1. They do form a basis for R2 because any vector that's in R2 can be created as a linear combination of these vectors. But if I wanted to get a vector over here, well, what would I do? Well, I'd scale this first vector to be a negative by some amount, and I'd scale this one by a similar thing as well. Right, so for instance, in particular, suppose that I wanted to get right here. Well, how could I get right here? Well, I think about moving along this x-axis until I reach a point where if I follow this direction, I can get up to that vector. Right, so this is just a scaled version of the first vector, 1, 0, and this is a scaled 1, 1, because it points in the same direction. So in order to get here, I can add up this plus this, which is a scaled version of the first plus a scaled version of the second. So any point, I can use those two vectors to get to. So in fact, they do form a basis, and they're linearly independent because they point in different directions. So the coordinates of a vector relative to a given basis are simply the scaling factors that you've got to use in order to get there. And so how much do I have to scale the first vector, and how much do I have to scale the second vector in order to get to where I want? So I'm going to make that more precise. So definition, if V1 through Vk is a basis for H, for a subspace H, and the vector x, let's say B, and B is in H, the coordinates of B relative to the basis, we usually have something like a script B if I'm talking about a basis. The basis V1 through Vk are, here's our notation. We're going to put whatever we call these things, brackets around the vector B, and we're going to put a subscript of B to say that this is the basis V1 through Vk. And what it is, it's the vector x, which is going to be x1 through xk, where x1 v1 plus x2 v2 plus xk vk equals the vector b. So B is in H, which means B is a linear combination of these vectors, which means I can scale these vectors by some amount and get to B. Whatever those scaling factors are, I put them into a vector, and I call that the coordinates of the vector B relative to the basis script B. And really, that's just formalizing what we just saw in a picture before. It tells you how much you have to follow each vector in order to get to where you want. Now, as far as actually finding them, let's find the coordinates. Okay, so let's let H be the span of the following vectors. these are vectors in R3, or in R4. So let's first note that if I took these as a matrix and I row reduced, what I get is oops. Remember that there's a small problem with the calculator. If you try to row reduce a 4x3 matrix, it doesn't work. It'll give you a dimension error. You need to add a column of zeros so that it's at least as many columns as there are rows, and then ignore the extra column of zeros at the end. But if we do that and we row reduce, what we get is the following. So if we row reduce this matrix, this is what we get. We get a pivot in every column, which means that these vectors are linearly independent. All right, so vectors are linearly independent, which is good because in order to be a basis, we need to be a spanning set, which it is by definition. We're saying the span of these vectors, and they also need to be linearly independent. So the vectors are linearly independent, and we get a spanning set, which means that we can look at the basis given by these vectors. So H is the span of these vectors, which then also correspond to a basis. All right, so now we're going to do two things. Save those vectors up there. Let's do three things. Is this vector x in H? Is that vector in H? The answer to that question is, right, so what does it mean to be in H? It means that I need a linear combination of those vectors. So I'm looking for C1, let's call this V1, V2, V3. So I'm looking for C1, V1 plus C2, V2 plus C3, V3. Scale versions of those vectors that better get me to the vector x. So that's saying, in terms of, this is a matrix equation, which is saying 1, minus 2, 1, 0, 2, 3, 0, 1, 1, 1, 2, 1. The constants correspond to the vector x, 1, minus 1, 3, 1. And then we need to row reduce. So if we put that in, and row reduce, what we get is the following. Now, remember that this last column corresponds to our constants because we've added it. This is a system of equations. So the last column is the constants column. So that last row reads 0 plus 0 plus 0 equals 1, which is inconsistent. So when looking for the scaling factors that I can attach to these vectors in order to create the vector x, we get an inconsistent system, which means that there are no scaling factors that work. So the answer to this question is no. No scaling factors work. X is not in H. Next part. So for the next question, let's ask, is this vector 5, 1, 0, 1 in H? So it's the same thing. We need to do the same thing. 1, minus 2, 1, 0, 2, 3, 0, 1, 1, 1, 2, 1. That's the vectors of the spanning set of the basis for H. And then we're asking, can I make linear combinations of those, which make the vector 5, 1, 0, 1. We reduce, and here's what we get. And now we notice that this system is consistent because the final row is not 0 equals 1, it's 0 equals 0. And that's okay. So this system is consistent. This corresponds to, so remember, well, this was really our C1, C2, C3, the constant, or the factors, the scaling factors that we could put on these vectors. And so we get that C1 is 2, C2 is 2, and C3 is minus 1. So we notice what that means is that 2v1 plus 2v2 minus v3 from those vectors actually equals our vector x, 5, 1, 0, 1. And if you plug those values up in there, it works. 2 and 2, that's 2 and 4 makes 6, minus 1 makes 5. And the rest will work as well. Right, so the 2, 2, minus 1, which we see right here, are the scaling factors that we need to attach to our basis vectors v1 through v3 in order to create the vector x. So the answer to this question is yes. Because I get a consistent system, x actually is in H. Finally, part C. Let's find the coordinates of x relative to the basis b, which is these vectors. So we've already done that. The coordinates of x relative to b are just the scaling factors that we need to use in order to make x out of v1, v2, v3, which is 2, 2, minus 1, 2, 2, minus 1. All right, that's what we need to say about sections 2.8 and 2.9. So check out the homework and quizzes, and see you next time.